Hello, students. Um, I really want to talk about some numbers now. So what do we know so far? Well, we've talked about bases, and we know that we can extend an independent set to form a basis for a set that they're in, and we can sort of do the opposite. We can take away vectors to form a basis for the span of those vectors. So we have the idea of adding and taking away, adding and removing, so we have these things, but we also have one result that's very specific in regards to talking about numbers, and that is that if you have the span of n vectors, any independent collection in that span has to be size n or less. So we have something that has to do with adding, subtracting, something that has to do with less than or equal to. I really want to attach a number to a basis. But before we do that, we do have to explain why such a number would be unique. So maybe let's do that next. So what I want to do is I want to say any two bases let's say, should I give them names? We'll give them names. I have to name them B and C. B and C for a vector space must contain the same number of vectors. So, no variance in the number. Okay, so how do we prove that? Well, let's suppose that the size of B is lowercase b and the size of C is lowercase c. So we have two different bases. Now remember what that means. These are linearly independent sets that span the vector space. So we have two different bases for this vector space. Okay? So what do I know? Well, I know that the vectors in B, all the vectors in B, are in the span of the vectors in C. Remember, C is a collection of vectors. It's not a set. It's a collection of vectors. So, there's some C1, C2, C3, but I'm writing it as C for the whole collection. So the vectors of B are in span C, and they're independent. So remember what we said. We said we have any independent collection inside the span of n vectors. I know that collection must be size n or less. Since these are independent, that means there has to be C or fewer vectors in B. Okay, that's one direction. But what else do we know? Well, we know the vectors in C are in the span of the vectors in B. So by that same result, the vectors in C are independent and they're in this span with size B. So the size of C must be less than B. These are also independent. So C is less than or equal to B. And what does that mean? Well, if B is less than or equal to C, and C is less than or equal to B, and that's what we wanted to show. They have the same number of vectors. So, doesn't mean that there's a single basis. There are lots of ways in general to choose a basis for a vector space. But no matter how you choose that basis, it will always have the same number of vectors, no matter what you do. And simple proof, though it relies heavily on what we did before, I guess as a simplest example, if you take Fn. No, that's what we want. We want n copies of f. So this would be the set of A1, A2 through AN, so that each of the AI are in F. And we know that we have one basis for this that we could make. How do we know that? Well, one basis, let's let B be the collection of 1, 0, 0. So we start with a 1, and then we put a 1 in the next slot, and then we put a 1 in the next slot. I'll put a 0 there. And so on. So I know this. Okay, so I know this is a collection of vectors that are all in f to the power n, right? So the n tuples. What do I know about this collection? Well, they're independent, and how do I know that? Well, because if I have alpha times the first one, plus, I want to do alpha 1, plus alpha 2 times the second, and so on until I get alpha n to the last. Well, if this equals 0, then what do I know? Well, this happens to be equal to alpha 1, alpha 2, alpha 3 through alpha n, and this has to be equal to 0. So I know that alpha 1 and alpha 2 and alpha 3 and all of these must be 0. That's the only way that these two things can be equal. So what does this tell me? Well, it tells me that these vectors are independent. But they also span the entire set. And how do I know that? Well, because if you have anything of this form, you can write it as linear combinations of these vectors in B. But any vector in f to the n is of this form by definition, because these are just the tuples. So we have a linearly independent collection of vectors which spans the entire space. Therefore, this is a basis. So this is one basis for f to the n. So what have we found? We have a basis for f to the n with n vectors. Now, is this going to be the only basis for f to the n? I mean, maybe if I'm in a field with only 2 elements and n equals 1, we can really like try to force, a strange situation. But unless we're doing something like that, no, there's going to be tons of bases out there for this vector space. But this is a vector space that has this as a basis, so therefore any other basis we pick is going to have the same number of vectors. So we're always going to have n vectors. So I'd like to now give that a name because we should call that something, right? I have a vector space and I want to say, instead of saying each time, well, we have a basis for this vector space with n vectors, and any other basis also has that same number. That's a lot of words. So let's give that a name, but let's introduce that definition in the next video.